So section 4.6 is some application problems of these exponential functions. And in a lot of them, you're going to end up converting back to logs. And I really like this section. I think it's maybe my favorite in the whole course because you really get to see some real-world applications of these exponential functions and how to solve them and why we need them. Because they're able to solve some pretty fancy equations and some pretty fancy problems by making use of it. Lots of science applications and some physics and chemistry and some different things that I think are pretty cool. Okay. All right, just as a reminder, one thing that may happen, these are called literal equations, and one thing that may happen, like in a formula, notice it says solve for D. So the formula says S equals 23.5 plus 2 log D. So this equation has two variables in it, S and D. Normally we can't solve equations for a single number if there's two different variables. So what they're asking us to do is rewrite it so that instead of having S by itself, we have D by itself. So our answer here is not going to be a plain number like 7. It's going to be D equals blah, 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 and it's going to have an S in it. Okay? All right, so if I want to get this D by itself, I've got to isolate the log portion, which means I'll have to get rid of the number first. So minus 23.5 on both sides of the equation, and we'll have S minus 23.5. That's not a number. I don't know what it is because I don't know what S is worth. But that's what will be on the left-hand side, equals 2 log D. Now, we're trying to isolate the D. Before we can get D by itself, we'll have to get log D by itself, so we'll divide both sides by 2. So S minus 23.5 divided by 2 equals log D. Now, notice that log does not have a base written on it, so it's implied to be 10. So if I want to get D alone, I'm going to have to get it out of log form and convert to exponential. So the base of the exponent's the base of the log. This base here is 10, even though it's not written. We know it's there. So 10 to this thing over here, S minus 23.5 divided by 2 equals D. Now notice that's a fraction exponent there. The exponent on the 10 is S minus 23.5 over 2. So make sure that even the divide by 2, it's clear that that's in the exponent position. Okay? Now if we suddenly knew what S was, if they suddenly said, oh yeah, S is 7, then I could type this in with 7 in the place of S. I could type that in my calculator and out would come the numerical value of D. Okay? All right, number 2, similar example. They want us to solve for x. Now notice there's a couple of variables here, n and x. Those are both variables. They want us to get x alone. Remember, e in this case is not a variable. E is the number e, Euler's constant. Okay? It's also got a variable of t. So if I'm solving for x, first I need to get the exponential part alone, e to the nx. So I'm going to get rid of the t by adding a t on both sides. 3 times e to the nx equals t plus 4.2. I don't know what t is, so we'll just leave it as t plus 4.2. Then I need to get the exponential part alone, e to the nx. So we're going to divide by 3. E to the nx equals t plus 4.2 divided by 3. Remember, e is a number, okay, not a variable, but we need to get the x by itself. We're going to have to convert to from an exponential to a log so that we can get the variable part by itself. So log base e of this thing equals the nx. Instead of log base e, we're going to write ln. ln means log with the base of e. So ln of t plus 4.2 over 3, notice that the t plus 4.2 over 3 is my argument, equals nx. And then to get the x alone, we need to get rid of the n, so we'll divide both sides by n. So our answer will be x equals ln of t plus 4.2 over 3 all over n. Notice that that t plus 4.2 over 3, that fraction is my argument, so I put it in parentheses there. Sometimes people don't like this fraction within a fraction. That's called a complex fraction. So instead of that whole thing divided by n, remember dividing by like 2 would be the same thing as multiplying by a half. So what you could do is say 1 over n times ln of t plus 4.2 over 3. And that would mean the same thing. Okay. All right. I want to show you really quick, even though it's not in your notes, I want to show you a couple of other word problems that are going to be like what you're going to see on your homework, just because they're a little different. And if you use the help features, it's going to be a little different in how I would normally work it. So I want to show you what that looks like, okay? One of them is pH equals negative log of H positive, okay? So this is not P times H. This is a real-world example of a problem. There's one like this in your homework. pH has to do with how acidic something is, like orange juice or you know, whatever the liquid is. I guess it doesn't have to be a liquid. But how acidic something is, and we have a scale, and that scale is based on logs. So this P and H are not a little p times an H. Okay, it's just one variable, pH. And then the H positive is, I think it has to do with hydrogen or something, but that's a separate variable. So this H plus and this H they're not the same, okay? And they ask us to solve for H positive. In other words, they want us to get the H positive by itself. All right, well, before I can get the H positive by itself, I'm going to have to get the log portion by itself. So this negative out in front really is saying negative 1 times that. So I would divide both sides by negative 1. So negative pH equals log of H positive. And then if I convert this to a log, if I convert from a log to an exponential, I should be able to get the H positive by itself. So even though they didn't write it, the base on this log is 10. So 10 to the negative pH will equal the H positive. And if you type that into your homework, it'll take that, okay? The other one that's in your homework that I thought might help is A over P. Oops, I'm sorry. Not A over P. It's just A equals P times 1 plus R raised to the T. And this hopefully reminds you of the compound interest formula that I think we looked at a couple of sections ago. And they ask you to solve this one for T. In other words, they want you to get T by itself. Okay, well, this is an exponential, and if I want to get T by itself, first I'm going to have to get the exponential part, the 1 plus R to the T by itself. So I got to get rid of the P, so I'm going to divide both sides by P. A over P equals 1 plus R to the T. Now, my preference at this point would be to convert it from an exponential to a log. My preference would be to say, oh, log base 1 plus R of the A over P equals T. That would be my preference. I've gotten T alone. And if this were a paper pencil test and you wrote this on your paper, I would give you full credit, okay? However, in your homework, they don't give you the option, and when you're clicking on the icons to type in your answer, they don't give you a plain log option. They only give you an ln option. So we're going to have to come up with an alternative way of writing this using the ln button that they will give you in the icons. All right, so remember when we first solved equations in the previous section that we said, hey, you know, you can do whatever you want when you're solving an equation as long as you do the same thing to both sides. So you could add 7 to both sides, or you could divide by 3 on both sides, or you could square both sides. You can do whatever you want as long as you do the same thing to both sides. So based on that, I am going to take the ln of both sides. I'm going to take the natural log of both sides. Okay? That's a legal move as long as I do it to both sides. Okay? And then I would say, you know, as long as I can make use of my log property here that says that these exponents can get pulled down in front of the argument. So that would give me ln of A over P equals T times ln of 1 plus R. And keep in mind, I've got to have that 1 plus R in parentheses to show that that whole thing is my argument, not just the 1. And then if I want T by itself, I need to divide by ln of 1 plus R, okay, to get rid of the ln of 1 plus R. So T is by itself, and on the other side, I have ln of A over P. You could put that in parentheses to show that whole fraction is an argument, divided by ln of 1 plus R. And you will need the 1 plus R to be in parentheses to show that that entire 1 plus r is your argument. If you leave off those parentheses, it will think that only the 1 is in the argument. Okay? And it will take that as an answer, and you will be able to type that in using the icons that they have available on that question. So I just wanted to point that out to you because that one is kind of a strange one on the homework, and I didn't want you to be confused. Okay, some other application type of problems that you're going to see on this section have to do with exponential growth and decay. And they give us this kind of essential formula they suggest that we memorize. A of t is your amount at some point in time. So generally some point in the future, 5 years in the future, 2 weeks in the future, whatever. So A of t is the amount at some future time. Okay? Future time t, whether it's 2 weeks or 6 months or 5 years or whatever they tell you your time units are. A sub 0 is the original amount. So if you started with 500 people, maybe it's you're studying a population in a small town, and there's 500 people in that town. Your A sub 0 would be 500 because that's the amount of people that you're starting with. And then A of t would be the amount of people at some future point in time, 6 months, 2 years, whatever. E is not a variable. E is the number, that 2.7 number, okay, the Euler's constant. K is the growth rate, okay? So if we say that the population is increasing by 3% a year, then our K would be 0.03. It's going to have to be as a decimal. Now what's interesting about this is if K, or your rate, is a positive number, that means the population is going up. It's increasing. The graph would be going up. If K is a negative number, then that means your population is decaying or decreasing, and it would look like this. Okay, so whether or not that K is positive or negative is going to tell you which direction the graph is going as time goes by. And then T is time. Now, when we do financial problems, T is typically years. Remember our compound interest formula? T was in years, whether it was the PERT one or the compounded periodically formula. But when we're dealing in other scenarios like populations of people in a town, populations of bacteria in a petri dish, something like that, your time might not be years. It might be weeks or hours or months or whatever. So you'll just have to read the problem for what kind of units the T is in. Now, this seems like one more formula to memorize, okay? We learned the compound interest formula, okay? We learned that one. And we said, hey, that's if it's compounded periodically, like, you know, once a year, 3 times a year, or whatever. If something is compounded continuously, we use the PERT formula. I want to point out that this exponential growth and decay formula is essentially the PERT formula. Okay? P was your principal when we were dealing with money. That's your starting population if you're using the A sub O. Then it's got the E. The T is still time. And then the R has just been replaced with K if it's not money. So sometimes instead of trying to memorize this third formula, I just think of it as PERT. If something is continuously compounding, these formulas are exactly the same. I could use either one. So I just kind of think about it as PERT because money is typically not compounded continuously anyway, but populations do change continuously. You know, if it's a human population of a whole nation, let's say, babies are continuously being born, people are continuously dying, people are continuously moving both in and out of that country. So it is a continuously changing population. So I can think of it as using the PERT formula or this other formula that they just mentioned in our notes. I prefer to just think of it as PERT. Okay? All right. A couple other formulas that we'll use, and I'll kind of show you why they work a little bit later. If they ask you how long it takes for something to double, example, how long will it take for your money to double if you invested in this account? Or how long will it take for the population to double? You can still use this formula over here. I would use PERT. Okay, you could still use that one. Or as a shortcut, you could say, hey, T, the time it will take for the population to double, equals ln of 2 divided by R. Okay, R is the rate again. So either one is fine. This is one more formula to memorize, so some people sometimes just like to stick with PERT. But using this formula does save you a little time, and I'll show you some examples in a minute. Radioactive decay. This is getting into a chemistry example called half-lives. Okay, so you may, if you've taken a chemistry class before, you may have said, oh, how long does it take for a material to decay, for half of it to decay? And however long that is for half of the material to decay is the half-life. For most materials, it's a very long time. Okay, if you think about radioactive materials that they use in nuclear weapons and things like that, the half-life is a very long time, thousands of years. So it might take 1,000 years for half of a substance to decay. If I had 50 grams and the half-life was 1,000 years, then 1,000 years from now I would be down to 25 grams. And after another 1,000 years, I would be down to 12.5 grams because only half of it decays every 1,000 years. Okay? For other materials, it's a shorter amount of time. Okay? For example, a lot of medications in our body, the half-life may only be a few hours. Okay? And our body filters half of it out every 3 or 4 hours. That's why you have to take another dose of the medication a day or two later. So, but that's the idea behind it. Notice this formula is exactly the same. It's still our PERT formula. Still the PERT formula. They're just reminding you that your K or your R, whichever you're using for rate, is going to be less than 0. It's going to be a negative number because the amount of the object is decaying. It's decreasing. Notice it will level off and approach 0. Okay? If I kept cutting this amount of the substance in half, from 50 to 25 to 12.5, then it would go to 6.25, and then 3 point something, and then a little less than 2, and so on. I would technically never get to 0. Now, it would eventually get to such a small amount that it might as well be 0. It's such a small amount that you can't even hardly count it or recognize how much there is. It's basically 0 for practical purposes. But technically, the amount will never get to 0. It will approach 0 but not get there. Okay? When we're working with these half-life problems, again, just like with the doubling, we used ln2 over r. Your half-life time, the amount of time it takes for half of it to decay, would be ln 0.5 or ln 1/2 divided by the rate. And similarly, if they said, hey, what's the decay rate if the half-life is 1,000 years, the rate would be ln of 1/2 divided by 1,000, or however long the half-life was. And we'll see some examples like that in a minute. Okay? As you're working through these problems, it's important to keep in mind what they're asking you for, to really look at those questions carefully. If they say how much will or what will the be, then they're probably asking you for the amount, whether it's the amount at the beginning or the amount at the end, whether it's the P or the A sub T. P would be the amount at the beginning, A of T would be the amount at the end. So same thing, if they said, what's the amount now? They're asking you for the P, the starting amount. If they ask you a question about time, when will it be? How long will it take? They're asking you to find T. And if they say something like, what's the rate? They're asking you to find R. Or K, if you're using the K formula instead of the R formula. Okay? Okay, so let's look at some examples here. Sam wants to buy a car in 5 years. I'm hoping Sam is maybe young, because if he's waiting 5 years to buy a car, probably a lot of things will happen. So hopefully maybe he's young teenager and is wanting a car when he gets to be a little bit older teenager. Maybe that's his plan. He wants to buy a car in 5 years. What amount must be invested now to have $12,000 in 5 years? So he wants it in 5 years. So how much does he need to invest now so that when it's 5 years from now, he'll have $12,000 to buy his car? They mentioned that the interest rate is 8% compounded semi-annually. Now, one of the things we have to be aware of is when we're using PERT and when we're using this other formula, the compound interest formula. Remember, PERT is used when we have continuous compounding. This formula is used when we have compounded every so often. Compounded on a schedule, like every year, every month, or every 6 months, or whatever. Since they mentioned that it's compounded semi-annually, we're using this formula. We only use the PERT one when it's compounded continuously. They do not say continuous compounding, so we're using this formula. Okay? All right. So that's our formula that we're using. We need to know what all these variables stand for. So let's read through the problem. He wants to buy the car in 5 years. That's a time. So we know T is 5. We're going to put 5 in for this T. What amount must be invested now? That's the principal. Okay, and they ask us, what is that amount? That must mean we don't know the principal. We're looking for it. That's what we're solving for. To have $12,000 in 5 years. So that's the amount at the end. The amount at the end is going to be $12,000 at a rate of 8%. Rate is 8%. Remember, we always have to use that as a decimal. And compounded semi-annually. How often it's compounded, that's our N. Semi-annually means 2 times a year, so N is 2. So now that we know these variables, we'll plug them in. A is 12,000. P is what we're looking for. R was 0.08. N was 2. Raised to the 2 times 5 because T was 5. Okay? This is the equation we're solving, and we're solving it for P. In my calculator, I can type in this portion over here, the 1 plus 0.08 over 2 raised to the 2 times 5. I can type that in my calculator. So parentheses, 1 plus 0.08 over 2 raised to the 2 times 5. If you're using an 83, you'll need to put 2 times 5 in parentheses so that it knows that entire 2 times 5 is in the exponent position. Okay, so I've got 12,000 equals P times 1.4802 blah, 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 blah. Okay? Now notice, this decimal goes on a really long time. Okay? I cannot just round it off and call it 1.5. If I round it off to 1.5, I will lose accuracy throughout the rest of my work. So I'm going to write down 4 or 5 decimals, but notice in my next step that I'm actually going to use the entire value all the way out to the 5. It really goes beyond this 5. I'm going to use that whole thing. Okay? So now, solving for P, I'm going to divide by both sides by that 1.4802 blah, 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 blah. I'm only writing, 4 or 5 decimals, but when I type it in my calculator, I'm going to go for the full value. Okay, that will get P alone. In my calculator, I need to do 12,000 divided by this big old long decimal. So 12,000 divided by. Now, if you are using an 84, instead of retyping that whole number, you can hit your up arrow, and it should highlight that number, and then when you press enter, it will paste the entire thing so that you don't have to type that entire value. Okay? So 12,000 divided by, I arrowed up and grabbed it and hit enter and it pasted it. Okay? And I get P equals 8106.770025. Okay? If you have an 83, 12,000 divided by, it does not give you the option to up arrow, okay? So you would probably need to type it. Type that whole thing, 14802442285, in order to get that same answer. Your other option, I went back, when that was still on my screen, oops. 1 plus 0.08 over 2 raised to the 2 times 5. If you're using an 83, when you had this number, your other option is to take your 12,000 divided by, and the little negative key next to the enter, right above it, it says in blue ANS, that means answer. So to get to that, you would hit the second button. So you could hit second answer, and it says, oh, you want me to take 12,000 and divide by that last answer I had. And you say yes by pressing enter. So that keeps you from having to retype the entire 1.48 number, But that only works when the very last thing on your screen was that 1.48. When that was the last thing on your screen, then second answer would paste it in for you. Okay? Either way, 8106.77. Now remember, what does this stand for? This is how much money Sam needed to invest. This is his principal. This is his starting amount. So if he wants to end up with $12,000 in 5 years, then now he needs to invest $8,106.77. Okay? Now, how did I know to round it to that? Because this is money, and money we round to the nearest penny. So 2 decimal places. Even though the prompt didn't tell me to round to 2 decimal places, I know that I need to because this is money. And money, we go to 2 decimals. Okay? So notice what that means. If he invests $8,106 now and 77 cents, then in 5 years he will have $12,000 in his account. How did he make that other $4,000? Nothing, by just having an investment and not taking the money out, just leaving it invested. Okay? So that's kind of the whole idea behind retirement accounts and those sorts of things. You put money in now and you just leave it alone and let it grow, and it will be worth a lot more money at the end when you need it. Okay? All right, another example. When will an investment of $500 grow to $750 if it is invested at 4% compounded continuously? Notice they said compounded continuously. Continuously means I use the PERT formula. Okay, so hopefully you notice the difference between number 3 and number 4. Why number 3 used the regular compound interest and why 4 is going to use PERT. Okay, let's read through and identify what each variable is. An investment of $5,000 grows to $750. So the $500 grows to $750. So $500 is our starting amount. It's our principal. The amount at the end, the A, is our $750. 4% is the rate. And their question to us was, when will it happen? When is a time. So we're looking for T. T is the one that we don't know. Plug those values in. So 750 equals 500 times e to the 0.04t. This is an exponential equation. We're solving it for t. To solve an exponential, I need to get the exponent part by itself, so I need to get rid of the 500. I'm going to divide by 500. In my calculator, I'll type 750 divided by 500. I got 1.5. So 1.5 equals e to the 0.04t. We have isolated the exponential. Now we need to get the exponent by itself. So that means we will convert from an exponential to a log. Log base e. Okay, but when your base is e, we don't write log, we write ln. ln means log with a base of e. So ln of 1.5, 1.5 is my argument, equals 0.04t. Now we just need to get t alone. To get t alone, we get rid of the 0.04 by dividing. So we'll divide both sides by 0.04, and that will get t alone. In our calculator, we can type ln of 1.5 divided by 0.04. So ln of 1.5, and then notice what I'm doing here. This 0.405 is my ln of 1.5. I'm going to hit division symbol, and that's telling my calculator, hey, take that last answer and divide it by 0.04. And I got 10.13662, blah, 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 okay? In your homework, it will tell you what to round to. Typically, when it's years, it might be tenth of a year. So in the tenths place, the 1, we just have to decide if that 1 should go up or stay, and it would stay at 1 because the number after it's less than 5. So it would take 10.1 years for this money to go from $500 to $750. So notice that means you made $250 in a little over 10 years, which is kind of a long time to have to wait for $250, okay? But your rate was only 4%. Some of the others, it was a higher rate, okay? And percentage-wise, you've still got 1.5 times your money. So if I'd started with 5,000, I would have gone to 7,500 in that same amount of time. So it is looking at the percentage growth there as well. Okay. Another example, how long will it take an investment of $450,000 to grow to $900,000 at 7% compounded continuously? When they say continuously, that's telling us that we can use the PERT formula. Okay, compounded continuously means we use PERT. Now I would point out we're going from 450,000 to 900,000. If you have $450,000, you got a lot of money, okay? And it's going up to 900,000, okay? All right, so we're using our PERT formula. As a reminder, we could be using this one. It's the same thing. I just think it's easier to remember PERT, okay? All right, so A is my amount at the end. 900,000 was the amount at the end. P is the starting amount or principal. That was 450,000. And our rate is 0.07. We're looking for time. They said how long will it take. So 900,000 equals 450,000 times e to the 0.07t. We're solving this equation for t. That means we got to get t alone. Before I can get t alone, I have to get the exponential part alone, the e to the 0.07t. So I've got to get rid of the 450,000. I'll get rid of it by dividing. $900,000 divided by 450,000 is 2. Notice what just happened. We're trying to double our money. From 450,000 to 900,000, that's doubling our money. All right, so 2 equals e to the 0.07t. We've isolated the exponential. We need to get the exponent, though, alone. Okay, so we convert from exponential to log. Log base e. Now, log base e, that's ln. ln of 2 equals 0.07t. And now to get t alone, we'll divide by 0.07. So t equals ln of 2 divided by 0.07. In my calculator, ln of 2 is a terrible, horrible decimal, but then I divide it by 0.07. So as soon as I hit the division symbol, it knew I wanted to take that last answer and divide by 0.07. And I get 9.9 if I round it to the nearest tenth of a year. Okay, so that means it will take 9.9 years for your money to go from 450,000 to 900,000. Okay? Now what I want to point out about that I think is kind of interesting is I doubled my money. From 450,000 to 900,000, I doubled my money. How long would it have taken if I wanted $5 to invest and I wanted to double it to $10? Now, $5 to $10 is still doubling your money. It still would have taken 9.9 years. And that bothers some people. They're like, but it's only $5. $5 to $10, you're making $5. Surely it won't take 9.9 years. Yes, it will. Okay, because that's what the growth was. We went from 450 to 900,000. We doubled our money. So if you remember, we said there was a shortcut formula. If all they ask you for is the doubling time, you could just take ln of 2 and divide by your rate. That's actually what we did here. Did you notice how once we took our 900,000 and divided by the 450,000 to get the exponential part by itself, we ended up with ln of 2. So as a shortcut, if we had really been watching and said, hey, 450,000 and 900,000, that's doubling our money, we could have just said ln of 2 divided by our rate of 0.07. That would have saved us quite a bit of work, and we still would have got this 9.9. So notice, if I wanted to go from $5 to $10, I'm doubling my money. So it would still take me ln of 2 divided by 0.07. It would still take me 9.9 years because it's still that doubling formula, which is really kind of interesting, I think, that whether you're going from $5 to $10 or 1 million to 2 million or 3 billion to 6 billion, it would still take you 9.9 years to double your money. Okay? I know a guy who works as an investment planner for people with their stocks and bonds and different things like that. And he says that they use something called the rule of 72. And basically that's saying if your time and your rate multiply to 72, that's how long it takes to double your money. So in other words, if you are invested at 8%, that's 0.08, it will take you 9 years to double your money because that multiplies to be 72. If you got 10% interest, it would take you about 7.2 years to double your money because that multiplies to be 72. So what's interesting about that is it's based on this LN formula that they're working with there. It's just that natural logs of 2 is not a convenient number to use in your head. But notice what happened here. 7% interest, 9.9 years, 0.07 times 9.9 is very close. I'm sorry, 0.07, not 0.09. 0.07 times 9.9 years is, about 70%. It's pretty close. So that rule of 72 that stockbrokers and things use, it's based on this formula right here. It's not a perfect match. This didn't come out to 0.72, it came out to 0.69, but it's close. And it's using that same idea of natural logs. That's where they get it from. Okay, so keeping that in mind, number 6, how long will it take $500 to grow to $1,000 at 7% compounded continuously? Hopefully you notice that 500 to 1,000 is doubling your money. So rather than use that PERT formula, we can use our time equals ln2 over the rate. So the time it will take is ln of 2 divided by the rate of 0.07. And I bet it's going to come out to that same 9.9 years, right? Because that's what we had before. So ln of 2 divided by 0.07. It's that same 9.9 years. Okay. How long will it take for an investment to double at 5% compounded continuously? Now, it is important to note that we can only use this ln2 over rate when we're doing compounding continuously. Okay, that's another reason the stockbroker formula rule of 72 is just an estimate, because in real life you don't get compounded continuously. Okay, but anyway. All right, so how long will it take an investment to double at 5% compounded continuously? So time equals ln of 2 over your rate. So ln of 2 divided by our rate of 0.05. ln of 2 divided by 0.05. And it will take about 13.9, if I round to the nearest tenth, years. Why does it take longer? Because my rate was not as high. Okay? My rate was not 7%, it was only 5%. So if they lower the rate, it will take more time for your money to double. And then number 8, see if you can figure this one out. How long will it take $500 to grow to $1,500 at 7% compounded continuously? So notice they're not doubling the money, they are tripling the money. So I bet instead of ln of 2, it'll be ln of 3 divided by your rate. So ln of 3 divided by 0.07 is 15.7 if we go to the nearest tenth. Why does it take longer? Well, a while ago when we had 7%, we were just doubling. So it took 9.9 years. But now that same 7%, we want to triple our money. So it should take longer than 9.9 years. It takes 15.7 years. So that's kind of an interesting way to look at that. I think that's a good stopping point for this first group, and then we'll do video part 2 for another type of application.